Hello, I want to record a video about the efficiency of the code that we are writing for our test automation activities, because sometimes we are dealing with big data or different data types or structures inside there are a lot of elements, and we are performing different operations like inserting, adding, removing, or maybe searching for some values inside those data structures. But how efficient we are implementing these algorithms? Because sometimes whenever we write our code, then the processing time is really huge, or maybe sometimes the resource consumption is not good, is not efficient. So how can we have an understanding of how efficiently we are implementing our algorithms, or how can we measure how efficiently we are writing this? I guess you already know what I'm talking about. We are talking about the complexity, because complexity is a direct measure of the efficiency of the code that we are writing. But we can think about two different dimensions of complexities. Actually, we have already discussed about those, so I can take some quick notes here. The first is the time complexity, and the second is the space complexity, right? Which means the first one is how much processing time we need to complete our algorithms or our processing, and the second is how much memory we are using to perform these activities. I want to discuss this over a practical example. So let's say in our example, I will code here as well. So let's say we have two different arrays. This is my first array having different numbers inside, and I have another array having some different values. What I want to do is just to check if these two elements have a common element, common value. So I will implement a function which will return, like, let's say, find a common value, which will return true if these two arrays have a common value, or otherwise it will return false if they don't have a common value at all. So I will send these two arrays to my function and print out the return value. Cool. So here will be my function, which will be find common value, which will accept two arrays and return either true or false, right? So the first thing that I can think of is I start with the first element of first array and then try to find it in the second array, and then if I cannot find, then I proceed with the next elements in the first array. So I'll scan the whole array and I'll go through all elements of second array, which will be like two inner loops. So let's try to do that. Like the pseudocode will be start with the first element of first array and try to find in the next array. If I can't find a common value, which means one element existing in the first array does not exist in the second array, then I will return false. So let's start with the first loop. It will be scanning the first array, start with the first element until the last. So I have a for loop here which will iterate from beginning to the end of the first array. Start from the first index, which will be 0, until the end of the first array, which will be length of the first array. And now, when I take the value of this element in the relevant index, it will be this one, right? First array is relevant element in the index that I'm looking for. So this value, this is the value that I'm looking for. I will look for this value inside the second array. So let's try to search for it. So for searching, again, I will start from the beginning of the second array. So I need another for loop to go from beginning to the end. Let's again start from 0 until the end of this second array. So if the value on the relevant index in the second array, which will be array 2, the relevant index is j, if this value is what I'm looking for, which was this one, then it means I already find what I'm looking for. I was looking for a value inside second array, and whenever I find it, then it means I'm done. So I can already return true, right? Because I'm looking for a value, I found it, so it means they already have a common value because it was already in first array and I found it in the second array, then I can return. Otherwise, if I don't return, which means if this condition is not met, then I can continue my search. So I can continue iterating over this loop. So if I complete this loop without returning, like without having this value that I'm looking for is found, then I can continue with the second iteration of the first loop, the outer loop, which means the first element of the first array is not found in the second array, so I can jump to the second element of the first array. And similarly, I go through the whole elements of the second array, and if I cannot find it, I will go until the end of the first array. And if I cannot find it inside the second array for all the values in first array, which means I complete these two loops, inner loops, without returning true, that means I could not find any common value. So in that case, I can already return false. Let me quickly check my code here. Okay, here I'm iterating through first array. Here I'm iterating through second array. It should work. Let's try to execute this. So this is my test.js file. Let's execute this. It returned false for these values. For example, let's add some more. It returned false. Let's have an example in which they have a common value, like let's say 12 is common, right? Now I expect it to return true. It returned true. Cool. This code is already doing what I try to do, what I try to accomplish. But how efficient this is? It has two different arrays, two different loops scanning through the whole arrays. So which means, for example, this will execute. By the way, the performance will depend on the situation, right? Because if these two arrays have a common value in the first indexes, like if 2 and 2, I will already return true in the first scan, which means in the first iteration. But if not, like if I have common values, as in this example, on the last indexes, I will scan through the whole array until the last index. So in this time, the number of operations or the number of match algorithms that I'm running will be n times n. So this loop will run n times n is the length of the first array, and this will run m times which is the length of second array. So how can I conclude if my code is efficient or not? Because as we discussed, it will depend on the situation, right? Because if we are really lucky, the two arrays may have a common value in the first indexes. But it will be the best case for us because it means we are really very lucky and our processing will conclude after the first iteration. It will not do anymore. So it will be the best case. It is called as big omega. And we have the worst case in which these two arrays have a common value at the last indexes. So in this case, we are really very unlucky. So our algorithm will run through different iterations until the last indexes. It will take some time. Whereas the worst case, it is called as a big O notation, because since we cannot have an idea about the performance of our code, since it depends on different situation, these are different metrics to measure our code efficiency or the complexity in different situations. If we are measuring our code performance or the complexity under the best case, then it means we are measuring the big omega performance. Or if we are measuring it under the worst case, then it means we are having a big O notation complexity. But these two cases are very rare, right? Best case or worst case. It is really very low probability. So there is another metric which is the average case, not best case or worst case, maybe having the common values in the middle of the arrays. It's called as average case, and the name in the terminology is big theta. Cool. And generally, big O is very common because we should be prepared for the worst case, right? If somehow we hit the worst case, then how efficiently the code that we have written will execute. So big O is generally used commonly. And in this case, how about the performance of this code that I have just developed? It will run in the worst case m times n, right? So let's say that m and n have the same values. So we just say n times n, which is the n squared. O n squared. So which is not really very efficient because we have two inner loops, and n times n is, if the n is a big number, then it will be a huge. For example, if n is 10, n squared will be 100. But if I had somehow accomplished writing a code which will have a on notation, on metric in big O notation, like if it was this, because as of now, the code that I have just written has a n squared metric, right? So it will be for n 10, it will be 100. But if I can somehow accomplish to write a code which will have a on complexity, then it will be 10. So, by the way, it might even 2n or 3n or like these are all considered as on, because while we if we, for example, if we consider a graph where we try to calculate the complexity, if n goes to infinity, then this coefficient doesn't matter too much, right? Because n is going to infinity, so we can just discard this coefficient. So these are all considered as ON. So now I will try to implement a code which will have an ON complex array. So let's try to do that. Let me deprecate this and I'll try to create another function, find common value, which will again take two arrays and return true or false depending on the situation. If they have a common value, it will return true, otherwise it will return false. So as a rule of thumb, the best practice is trying to avoid inner loops. So what I'll do is, first I will iterate through the first array. So I'll start from beginning of the first array until the end. Array first length. And I will record all the values to another array that I'll create. So let's create another array. Let's name it smartly, like I will record the values in the first array. How I will record is like the value in the relevant index of first array is array 1 in the relevant index, which is I. So this is the value. I want to record this value inside the array that I just created here. So I will mark the relevant index in that array that I just created as true, which means that value is seen in first array. So the index of the array that I created will be marked as true. For example, if I have a 2 value in the first array, because in this example I have 2, right? So whenever I see 2, I will mark the second index of the array that I will use for my algorithm as true. And then I will mark the fourth index as true as well when I'm going through this for loop. And then after I'm done, which means I mark the relevant indexes according to the values of the first array. And then I will go through the second array as well. So I'll have another for loop here. And now the values will be array 2 in the relevant index. This is the value, right? So if the index of the array that I created is marked as true at that index, which means the value coming from array 2 is marked as true, then it means it was already seen in the first array, right? So what I mean here is, if the index of the array that I just created for this matching algorithm is marked as true, all right, then I will return true. Otherwise, if I did not return true so far, then I will return false. which means I could not find the relevant value, right? What mistake I have here? It should be the square brace, right? To indicate the index. Cool. Let me try to execute and then I'll show you what I'm doing here by debugging. So, for example, let's change this. Okay, now this execution will hit this function that I've just written. So now I don't have n times m, right? Because I don't have inner loops, but I have two loops in sequence. So it will be 2 times n instead of n squared. So depending on n, the 2n might be even worse than n squared. I mean, if we are talking about 2n, it cannot be worse, but at least they can have equal performance. But like, depending on the case, if I have 3n, it might be even worse than n squared, right? If n is only 2. But since n would not be that much small numbers like 2 or 3, most of the time 2n or 3n would be better than n squared. So this is what we would prefer. And let's go back here. It had, in the worst case, it had, it means in terms of big O notation, it will have O n squared complexity. We are talking about time complexity, right? So this is its complexity. And how about this function? It will have O 2n, since we are discarding the coefficients and the constant numbers, it will be On, which is already better than the first one. So let's try to execute this one. Now I expect false because they don't have a common value. It returned false. How about if they have a common value? It returned true. Cool. Let me try to debug this to show you what I'm doing here. For example, let me try to debug. So whenever I execute this, now I have an array here, values in array 1. I don't have any value inside, but whenever I start iterating, first I mark the second index to true because 2 is coming from first array, right? And then let's continue. Now I marked index 4 as true as well. So values in array 1 is another array that I created, and it has already 5 elements inside because I marked index 2 and I marked index 4, which means the other elements are already marked as false. But it has already 5 elements inside. And let's continue. So actually, let me continue just until here. When I complete this, values in array 1 array is an array with length 12. It has some values inside, like all the other values are marked as false, but 2, 4, 5, and 11 indexes are marked as true. And when I do this check, like what is the array 2 at index j? J is now 0 because I just start iterating. It is 3, right? So I will check if an index 3 in the array that I created for comparison, which was values in array 1, was marked as true or not. 3 is not marked as true, so in the first iteration it will not hit this condition, so it will not return true. In the second iteration, now j is 1 and the value inside the first index, I mean index 1, in the second array is, where is it? It is 6. So is index 6 in values in array 1 is marked as true? No, so it will not again return true. So for index 7 is not marked as true. And now index 11 is marked as true in the array that I'm looking for. So it will hit this condition and it will return true. And yeah, I will print out the result, which is true in this case. So in terms of time complexity, we know that the first function that I created here had O(n) squared complexity, time complexity, but the second one has O(n) complexity. So the second already is doing better in terms of time complexity. But what is the disadvantage of this? Here in the first implementation, I was just modifying, or I even don't modify, but I was just reading the values inside the original arrays, right? I did not create any additional data structure or any additional memory. But here in the second implementation, I create another data structure here. So I'm using some additional memory, which means my space complexity now is worse than the first, because in the first I do not have any additional space or memory consumption, but in the second one I'm just creating an additional array on top of the original arrays and I'm using some additional resources. So in terms of time complexity, the second implementation is better, while in terms of space complexity, the first implementation was already better since I don't use any additional resources. So depending on the situation, like if memory usage or the resource usage, resource consumption is really very important for us, then we can, and if n is not that much high, then we can go with the first solution. But otherwise, if we are solely concentrated on the time, the processing time and the time complexity, then we can select the second solution. So always depending on the situation, we can select the best solution for us, and we can keep these complexity metrics in mind to conclude our best solution. I just made my IDE full screen just to use the whole screen, and I want to talk about the data types, because in the beginning of the video we said that we may have to deal with different data structures or data types, and we may have to do some different operations on these data types. So let's talk about some different data types that we might have to deal with. Starting with the linked list. I have a class here and I implemented different functions, but let me start with explaining you what a linked list is. So we already have an example here in which we dealt with arrays, right? So arrays have some indexes. We had some index here, index values, and we can just directly address to the relevant element inside the indexes. Linked lists does not have indexes, and it's at first it doesn't sound very convenient, right? If we have a chance to index all the values inside, then why don't we have it? Or why don't we do it? Because sometimes it has some advantages, but sometimes it has some drawbacks as well. So first of all, let me search for the visualization of linked list here. For example, linked lists. Yes, it looks something like this. So it has some elements inside, but instead of having some indexes, it addresses to the next element. So each node, each element has a next attribute. So we know after a value, what other value will come next. So this is the code, the relevant code to implement a linked list. So in the linked list, we have the head, which address to the first node in the whole linked list, and we have the tail, which is the last node, and we know the length. So whenever we just create a new linked list, we have one node, which is both the head and tail, and the length is 1. And for each node is another object actually. It has a value inside. So in the first node, for example, we know what value is there, and we know to which value it addresses, which means what value will come next to this node. So each node is addressing to a next node, right? So it was looking something like this. So each node has a next attribute. This is an object, and A, B, C, D, these are the values, and each is addressing to the next. So the head doesn't have a previous node, so it is already the first node, and the tail, in this case, the value of the tail is D. The next node is null because tail is already the last node. Cool. So I created a summary class here. Let's take some notes. We start with linked list. The attributes are head, tail, and length, right? Cool. And it has some nodes. Nodes are also objects, and nodes have values and the next feature. Cool. And what kind of operations we can do in linked list? There's a push operation. Push means adding a node to the end. So we are pushing one element to the end of the list. And pop means the other way around, like just removing an element or a node from the end. From end. What if we do the same operations like adding and removing to the beginning of the list, to the head of the list? Then it is called as shift. If we are just adding a value to the beginning, just previous to the previous head, which will be our new head. Oh, sorry, this is unshift. It's to beginning. And if we remove the current head and the next node will be the new head, then it's called as shift. So we are shifting to the next row, right? The current head will be dropped. Cool. How about the complexity of these operations? Let's think about this. So, for example, push operation, we are just adding a new tail, right? So basically we know the tail, we have the tail attribute here. So we can just, and next, normally its next was with, its next was null, right? So now we will fill that next attribute with a new node. So it's nothing but just adding a new node to the end. So it is just O1. We are not iterating through elements. We are not doing any other scan algorithm. We just go to the tail and add the next node. And pop as, again, we can just directly address to the tail, and we will just remove that, which means we can just remove tail. But now I'm thinking, if we want to remove, then we have to set a new tail, right? So the previous node should be the new tail. But how do we know the previous node? We don't have a previous attribute, so we have only next attribute for each node. We will come to that point. So if we are talking about double linked list, which means each node is addressing to the next and the previous nodes, then it would be much more easier. But in this case, since we don't know the previous node coming previous to the tail, we should just iterate until the end, which means it should be not O1, but it should be an ON operation. Because again, I'm repeating, we will remove the tail, but if we remove the tail, we should set a new tail, which was the previous to the current tail. But since we cannot directly address to the previous node coming previous to the current tail, we should start from head and we should go until the node which is coming just previous than the current tail. So it will require an ON operation. How about unshift? Unshift is, it was just adding a new node to the beginning, right? So we will create a new node and we will set next attribute of this node to the current head, because now this time our newly created node will be our new head, and from the new head we will do what? To the current head, we don't have to do anything. We will just change the head of the linked list to the newly created node and just address the next node to the previous head. That's all we have to do. So it will be just O1 operation. And how about shift? Shift is removing from beginning, which means let's try to interpret what this means. So basically we know the next node coming just after head. We know this, right? Okay, so this will be our new head because we will remove the previous head. And what else? We can just remove the next attribute of previous head. We can set this as null to just cut the bind between the previous head with the new head, right? So it will not have a previous node anymore if we cut this bound, which means we are setting this bind to null. So that's all. I think that's it. We will set the next node as the new head, which will be our head of our linked list, and we will cut the previous head. Yeah, that's all. So this is just again O1. We don't have to scan the whole list. So here, if we see, like only removing from end will require a scan operation. We should start from head until the tail. Why? What was the reason for that? Because when we cut the current tail, we have to set a new tail, and we cannot address the new tail, which will be standing at the end of the list, because the previous tail doesn't have a prev attribute. It just has a next attribute. So to be able to locate the last node in the new list after cutting the tail, we should start from head and we should go next until the last node, which doesn't have any next attribute at all. Cool. So considering and comparing this to the array, like if we consider the same for the arrays, what would these operations have? What complexities these operations will have? Let's see. So pushing to an array, which means we are adding a new node to the relevant index, right? We have this time we have the indexes, so we know the last element, we know the last index. We will just add one more, so it will be O1. How about removing from end? It will be again just setting the last index to null. How about unshifting, which means adding to the beginning, which means the array of first index, we know which address we should delete. Cool, this is not that much difficult. But when we remove this, all the indexes of all the other elements should shift, right? So we should do an indexing for all others. So this will be an ON operation. We should iterate starting from beginning, which beginning means the new start value, until the end. And whenever we remove from beginning, this was adding to the beginning, right? So, sorry, this was for removing. When we remove, all the other items will have new indexes, one minus than the previous. And similarly, when we add a new one, like we can just add easily a new value to index 0, but all the other values will have new indexes. For example, previously we had the value at the 0 index, but now that value have index 1, right? So it will be shifted. Adding to the relevant index is not a big deal, but we have to do indexing for all the other elements. It will be ON. So now we can understand, right, why don't we sometimes use just arrays but instead linked list? Because, for example, shifting and unshifting operations, while linked list has O1 operations or O1 complex arrays, arrays have ON complex arrays. So again, it will depend what kind of operations we are dealing with. Mostly, if we are doing most of the time shift or unshift operations, then we can go with a linked list, because linked list doesn't have indexes. We don't have to do this indexing operation for all the elements anymore. We just set the current nodes by modifying the next values, next attributes. Cool, let's move on. So double linked list, I just mentioned about it. It is just a little different from the linked list, in which the nodes has values inside and next nodes, next addresses, next pointers, and additionally the previous as well. For doubly linked list, it has a double link, right, to the previous and the next node. It has binds from double sides, both from the previous and the next. Cool. Let's proceed. What is the next? The next should be maybe the stack. So I had another class here. So let me show what stack means first. Again, let's see how it looks like. I think this is a good illustration. So whenever we add some items, it will go to the bottom of the bottle, right? So it means whenever we are adding some more items, it will be at the bottommost. So while removing, the item which we added first will be removed the last. This is important. Let's note this. Now we are talking about stacks. Stack is a first in, last out. like this. All right. And this is the code to implement a stack. We will have again different nodes. Each one will address to the next, and each will have some different values. And whenever we create this, we don't have a tail or head, but this time we will have a top value, which will be the node standing here on the top. Because this is important, because whenever we interact with this stack, we will be always interacting with the top value. We cannot reach to value 1. First, we have to remove 2, and then we can reach out to 1. This is why we only need the top value. Cool, let's think about different operations we can do for stacks. For example, for stack, we can add a value, or we can remove, right? So adding is just O1 operation, because we will add to the top. We don't have anything to do with the other elements. And similarly, remove is again O1. It is very simple, because we will not do anything with the other items. We can interact. This is the only chance we can do, right? Again, going to this illustration, adding or removing, always interacting with the top element. The others, we don't have a direct interface. First, we should do an add or remove, and then we can continue with the next items. So this is simple. And there is one more very similar structure, which is the queue. So this time, queue is not first in, last out anymore, but this is first in, first out. So whenever some different items lined in a queue, the first will go first. This is what queue means, as we already know. And for this, again, we have the add and remove operations. Both will have O1 complexity. Because we know, again, just like the stack, we know which one to add or which one to remove from the queue. We can do the same study for different data types, maybe including the hash tables or binary search trees, and we can go over different sorting algorithms, including bubble sort, insert sort, or merge sort. But I will just stop here not to make the video too long, and we can record another one. But today, the last reminder I want to do is using a cheat sheet, which shows this one, shows all the different metrics for different data types and different operations. We can see O1 is the most efficient, and the next is O log n. And if you remember the first implementation that I have done, it was O n squared, which was classified as horrible. It was not a good implementation, right? But the next one was O n, which is classified as fair, so which is way better than the previous one. So the summary of today's video is we discussed different complexity dimensions, including the time and space complexity, under different cases, including the best or the worst cases, and even in an average case, which is not the best or worst case, but in an average case, how efficiently, how well our algorithms or the implementations will work, how would be the efficiency of the code that we are developing. And we went over different data structures like array, stack, queue, how single and double linked list, how they're working, and what are the complexities for them. And again, we can go through different ones, and we can discuss the sorting algorithms in the next video. But for now, let me just say the key approach that we will try to follow in the sorting algorithms will be divide and conquer algorithm, because if we are trying to manage a very big or huge data structure, it would be much more challenging. But if we divide and try to merge them by sorting one by one, then it would be much more straightforward. For example, merge sort is following that approach. This is why it is not O n squared, but instead it has O n log n. Let me try to find if it is illustrated here. Yeah, here. So it will be something like this. First divide to smaller pieces and then merge them by sorting. For example, when we merge 38 and 27 again, we do it by sorting. This time when we merge them, now it is already sorted. So we don't have to sort anymore when we are dealing in the upper level. So let's discuss all the details in the next video, but for now, the summary was just following the best approach to reduce our complexities.